Chemical oscillators are reactions that, when far from their equilibrium point, will oscillate back and forth between concentrations of different reactants. They were discovered by Belousov in 1950 when he was working on the Krebs cycle and discovered that it bounced back between yellow and colorless. Later, a scientist named Zagorowski studied this reaction using malonic acid instead of citric acid. He discovered the mechanism of the oscillation. The cerium catalyst being oxidized, this increased the concentration of the cerium 4+ ion, which then reduced back with the malonic acid to the cerium 3+. However, there was also a bromide ion which inhibited the original reaction. Ce3+ no longer oxidizes. From there, the concentration of Ce4+, which is no longer being produced, decreased, which means the bromide ion also decreases because cerium 4+ cannot reduce back, producing the bromide ion. Then the original reaction is allowed to go again, and the cerium ion can again increase. This cycle was modeled by Field, Corus, and Noyes, called the Orogonator model. They used a mechanism of the reaction involving these steps. They then simplified the steps down and wrote out rate laws for each equation. From there, they were able to determine equations for X, which is the HBrO2. So if you see, it is being created in this one. Used over here. The third rate law is actually a combination of all three of those, and it ends up being negative. And then again, it gets used over here with a 2 coefficient, +2 K4 X squared. From there, using various simplifications, substitutions, and so on, they referred back to these equations. They made these substitutions, getting these equations. From there, these equations give a Hopf bifurcation. The system should oscillate if you start here, and this is what their model predicts will happen, and it should keep cycling forever. What you can also do is you can get a two-dimensional Hopf bifurcation by making a steady state assumption. This in chemistry is just assuming that an intermediate doesn't change much over time. So if you take dy d tau to be approximately 0, and then you can solve again for dx d tau. From here you can then set dx d tau to 0, and similarly set dz d tau to 0 to find the null lines. Which should give you something like this. Using Poincare-Bendixson, you can show that there is in fact a closed orbit. If you draw a nice big trapping region, finding that all the arrows in every region require to point in the middle. However, there's still your equilibrium point in the middle. So to get rid of that, all you need to do is draw a circle around here. And for any time in which this is a repeller, it will be a trapping region, proving that somewhere in here you have your hot bifurcation limit cycle. To determine that it's a repeller, you can find the Jacobian. From here, you can calculate the determinant, which from our graph, which uses, in this, Q equals 2, F equals 1. The determinant would be 1 plus -1/3, which is 2/3. This means it can't be, since it's greater than 0, can't be a saddle node. If you then find the trace, is approximately equal to 1 at this point, which is also greater than 0, also meaning that this must be a repeller for this value. You can determine that using this, you do in fact have a limit cycle using your trapping region of the box and a circle around, infinitely small around your equilibrium point. If you change your Q value, you'll see at Q equals 1, the equilibrium point disappears entirely. And at Q equals 5, if you solve for the linearization, you'll have an unstable spiral at this point, which is typical of the hot bifurcation. Another example of a chemical oscillator is the Brayler-Toski reaction, in which hydrogen peroxide reduces an iodate ion into iodine. Iodine is also oxidized back into the iodate ion by the hydrogen peroxide. The iodine ion can also react with malonic acid, and that creates an iodide ion. The iodide ion on itself is also colorless, but when it reacts with starch, it forms a blue complex. As you see, in solution A is a mixture of water and sodium iodide with sulfamic acid. Solution B is a mixture of hydrogen peroxide, malonic acid, starch, and manganese sulfate. As you can see, they oscillate from colorless, amber, to blue. And they keep repeating, and eventually, as most natural systems do, the solution will come to a deeper blue with the starch ion, and it will stay there eventually. A 10-step mechanism similar to the one shown for the Zeb-Toski reaction was proposed by Ren, Goa, and Yang. And using those steps, you can form similar overall rate equations for each of the components with the colors. And as you can see, they each rely on how the others are changing. These equations should give you a similar Hopf bifurcation oscillating between the three colors until one of the reactants, the other reactants that aren't shown, are used up entirely, in which case you end with your blue color.